Why is the universe expanding faster? Back in 1998, two independent research teams, the Supernova Cosmology project and the High-Z Supernova search team, made an astonishing discovery. By observing distant Type 1a supernovae, they found that the universe isn't just expanding, it's expanding at an accelerating rate. But how did they figure this out? Type 1a supernovae are known as standard candles because they have nearly the same intrinsic brightness. This property allows scientists to measure their distance from us based on how dim they appear. By comparing these distances to the supernovae's redshifts, which indicate how much the universe has expanded since the supernovae exploded, researchers unveiled a surprising trend. The farther away a galaxy is, the faster it's receding from us. According to the Hubble law, this was expected, but here's the twist. The recession velocity wasn't just increasing, it was accelerating. This defied the previous expectation that gravity from the universe's matter would slow down the expansion over time. Three members from these groundbreaking projects were awarded Nobel Prizes for this discovery, but their work was only the beginning. Further evidence has come from baryon acoustic oscillations and the clustering of galaxies, all pointing to the same conclusion. So what's causing this cosmic acceleration? Enter dark energy. Within the framework of general relativity, an accelerating expansion can be explained by a positive cosmological constant, lambda, which represents a mysterious form of energy permeating the universe. This dark energy started dominating the universe roughly 5 billion years ago, propelling galaxies apart at an ever-increasing rate. It's a key component of the current standard model of cosmology, known as the Lambda-CDM model, which also includes cold dark matter. In our quest to understand the accelerating universe, we turn to the evidence that supports this cosmic phenomenon. The rate of expansion of the universe can be analyzed using two primary methods: the magnitude-redshift relationship of astronomical objects using standard candles and the distance-redshift relationship using standard rulers. Standard candles, such as Type 1a supernovae, serve as beacons in the dark cosmos. These supernovae have nearly identical intrinsic brightness, allowing scientists to measure their distance based on how dim they appear. By comparing these distances to their redshifts, researchers can trace how the universe has expanded over time. In 1998, the first compelling evidence for acceleration emerged from these observations. The supernovae's redshifts revealed that the universe's expansion rate wasn't just increasing, it was accelerating. But supernovae aren't the only tools in our cosmic toolbox. The growth of large-scale structures, such as galaxy clusters, also provides crucial insights. In the early universe, before recombination and decoupling occurred, photons and matter existed in a primordial plasma. Points of higher density in this plasma would contract under gravity, creating sound wave-like vibrations. When decoupling happened around 380,000 years after the Big Bang, photons separated from matter, forming the cosmic microwave background. This process left shells of baryonic matter at a fixed radius from dark matter over densities, known as the sound horizon. As the universe expanded, galaxies formed around these inhomogeneities. By examining the distances at which galaxies cluster at different redshifts, scientists can determine a standard angular diameter distance, comparing it to predictions from various cosmological models. Recent discoveries of gravitational waves through LIGO and VIRGO have opened a new window into the universe. These gravitational waves act as standard sirens, providing a novel method to measure the expansion rate of the universe. In 2017, Abbott et al. Measured the Hubble constant to be approximately 70 kilometers per second per megaparsec using these waves. As we peer into the future of our ever-expanding universe, we encounter a realm filled with fascinating, albeit daunting possibilities. The relentless expansion of space means that the density of radiation and ordinary dark matter diminishes far more rapidly than that of dark energy. In models where dark energy is synonymous with the cosmological constant, the universe will expand exponentially, inching ever closer to a de Sitter universe. This exponential expansion spells a bittersweet fate. The cosmic microwave background, our window into the infancy of the cosmos, will be redshifted to lower intensities and longer wavelengths. Eventually, its frequency will drop so low that it will be absorbed by the interstellar medium, effectively erasing the evidence of the Big Bang from the observable universe. This transformative process will unfold within a time frame less than 50 times the current age of the universe, leading to the twilight of cosmology as the distant universe fades into darkness. As mass density continues to decline in a perpetually expanding universe with a non-zero cosmological constant, an intriguing yet somber scenario emerges. Over time, all matter will ionize and disintegrate, breaking down into isolated stable particles like electrons and neutrinos. The complex structures that once defined our cosmos will dissipate, leaving behind a universe in a state of heat death, also known as the Big Freeze. While this scenario paints a stark picture of the universe's ultimate fate, other possibilities remain on the table. Could we face a big rip, where the universe's expansion tears everything apart? Or perhaps a big bounce, a cyclical model, where the universe contracts and then re-expands? There's also the notion of a big crunch, where the universe's expansion reverses, leading to a colossal collapse. As we delve deeper into the mysteries of our accelerating universe, we encounter a multitude of theories that attempt to explain the elusive nature of dark energy. One such theory is Quintessence, which posits a form of dark energy with a non-constant state equation. Unlike the cosmological constant, Quintessence's density decreases over time, adding a dynamic layer to our understanding of cosmic expansion. Another intriguing proposition is the negative mass cosmology, which challenges the assumption that the universe's mass density is positive. This alternative finds a negative cosmological constant, suggesting a different framework altogether. Occam's razor, the principle that the simplest explanation is often the correct one, might favor this hypothesis. Dark fluid theory takes a different approach by attempting to unify dark matter and dark energy into a single concept. This holistic view could potentially simplify our understanding of the universe's accelerating expansion. Some researchers have even speculated that the acceleration could be due to a repulsive gravitational interaction of antimatter, or deviations from general relativity, such as the idea that gravitons themselves have mass, known as massive gravity. However, the gravitational wave event GW170817 has ruled out many of these modified gravity theories, narrowing down the possibilities. The back-reaction conjecture proposed by cosmologist Siksi Rasanen offers another fascinating perspective. This model suggests that the universe's rate of expansion is not homogeneous. Instead, we might be in a region where expansion is faster than the background due to inhomogeneities in the early universe. This creates walls and bubbles, with the inside of a bubble having less matter and thus a higher expansion rate. While not considered the most likely scenario, it remains a possibility that challenges our conventional understanding. Another possibility is that dark energy is an illusion caused by biases in our measurements. If we reside in an emptier-than-average region of space, the observed cosmic expansion rate could be mistaken for acceleration. A cosmological extension of the equivalence principle might also offer insights, suggesting that space appears to expand more rapidly in voids surrounding our local cluster. Finally, some theories propose that the accelerated expansion is an illusion caused by our relative motion to the rest of the universe, or that the sample size of supernova used in observations wasn't large enough to provide accurate results. Each of these theories, while speculative, brings us closer to unraveling the enigma of dark energy. As we continue our quest for knowledge, we must remain open to new ideas and evidence, ever vigilant in our pursuit of the truth.